All right, let's unpack this. We're diving straight into text embeddings today. These are basically the clever ways we get computers to understand language, right? Turning words, sentences into, well, numerical code.
Exactly. Think of it like giving every word its own unique address on a map. And words with similar meanings, they end up being close neighbors on that map.
Okay, yeah. And this is the magic behind so much of the AI we use daily. You know, search engines that seem to grasp what you're really asking, or chatbots that can actually make sense most of the time anyway.
That's a great way to picture it, definitely. But here's where it gets, well, really interesting. While these general language models are incredibly useful, they can sometimes hit a wall, especially when you apply them to very specific fields. Take telecommunications, for instance. It's just packed with its own special vocabulary, really complex ideas, and honestly, enough acronyms to make your head spin.
Okay, telecom. So we're talking about everything that makes your phone connect, right? The internet backbone, all that complex stuff behind the scenes.
Yeah.
And you're saying their language is like a totally different dialect.
Oh, more than a dialect.
Yeah.
Sometimes it feels like almost a different language entirely. I mean, consider a simple word like cell. In everyday chat, it could be, biological cell, maybe a prison cell.
Right.
But in telecom, it pretty much always means a coverage area for your mobile signal.
Okay.
Then you have sector. Could be part of the economy, or maybe a slice of a radio antenna's coverage.
Different meanings depending on context.
Totally. And don't even get me started on the acronyms. RAN, Core, MME, SMF, UPF.
Whoa, slow down.
Right. GNB, EMB, ORAN. It's like trying to decipher an alien code sometimes, truly.
Yeah, I can see that. And a general AI, one trained on like tons of regular internet text from Wikipedia or whatever, it wouldn't necessarily know that a GNB is the next-gen tech for a 5G base station. So if you're trying to search for info on, say, boosting your GNB performance, the AI might just get completely lost.
Precisely. It might think you're talking about something totally unrelated.
Sure.
And that's where our deep dive today takes a really fascinating turn. We're looking at a potential solution to this exact challenge. T-VEC, the Telecom Vectorization Model.
T-VEC.
Yeah, it's a text embedding model specifically designed from the ground up almost for the telecom world, developed by the folks at Neto AI.
Gotcha. So our mission for this deep dive basically is to figure out how T-VEC was built and, crucially, why it's apparently so much better at understanding telecom speak compared to your average general-purpose AI model.
That's the plan.
And for this exploration, we've got some really interesting excerpts from the actual T-VEC research paper, the tvec.pdf file. So let's jump in.
Sounds good. First off, I think it's really crucial to properly understand why those general models struggle so much in the telecom space. It's not just the unique words, though that's a big part of it. The telecom world is just constantly changing. You've got new technical standards popping up all this time. 5G, LTE was before that. Now people are talking about 6G.
SDN, NFV, more acronyms.
Exactly. Software-defined networking, network function virtualization. It's like trying to hit a moving target for the AI models. The ground rules keep shifting.
So it's not a field where things stay static for long.
Not at all.
Yeah.
Then you have the incredibly complex ways these networks are actually put together. You hear about the radio access network, or RAN, the core network, the transport network. Each one is a whole world with its own concepts and terms.
Okay.
And beyond just the pure tech, there's this whole other layer of specific operational jargon. Things like handover, which is when your phone switches smoothly between cell towers, or RRC states, the different modes your phone can be in to save power or signal readiness. QoS parameters determining how good your connection quality is.
Right, quality of service.
Exactly. And finally, sort of layers on top of all that, you've got this dense web of regulations that the industry has to follow. It's a very particular, very intricate world.
Wow, that paints a really clear picture. So trying to use a one-size-fits-all AI model here, it's kind of like trying to fix a super complex Swiss watch with just a basic wrench set, maybe.
That's a spot-on analogy. You might get somewhere eventually, but it's probably not going to be very efficient, and you're definitely not getting the best results.
Okay. So how did Neto AI actually tackle this? You mentioned deep fine-tuning. What does that involve?
Right, so they developed TVEC through this process they call deep fine-tuning. And this wasn't just a quick tweak. They started with a really powerful state-of-the-art general-purpose model. It's called GTQI 1-1.5B Instruct.
GTQI 1-1.5B Instruct.
That sounds pretty heavy-duty.
It is. Think of it like starting with a top-of-the-line general-purpose race car engine. really powerful, but maybe not optimized for, say, off-road telecom terrain.
Okay, so they took this powerful base engine, and then what did they do to customize it specifically for telecom? They made three really key contributions, three big moves to properly mold it into TVEC. The first, and maybe the most foundational, was creating a very carefully curated telecom data set.
Okay, data set, but not just grabbing random telecom documents.
No, definitely not.
Yeah.
This took over 3 months of intensive manual effort by actual telecom domain experts at NetOAI.
3 months? Wow.
Yeah, it highlights the effort. They specifically generated relevant text pairs and, importantly, triplets designed to teach the model the real nuances of telecom concepts.
Okay, pairs and triplets. What kind of information went into this special data set?
They really aimed for broad coverage across the entire telecom universe. Think about the evolution of mobile tech, 3G, 4G LTE, the current 5G, new radio or NR, even Wi-Fi standards.
Right.
Then the different parts of the network access, the RAN we mentioned, the core network, which is like the brain, the transport network moving data, even the OSS, BSS systems for running the business side.
Okay, comprehensive.
Very. They included specific network functions, those acronyms again, like AMF, SMF, UPF, GNB, ENB. Also, operational procedures, how networks get fixed when something breaks, how performance is monitored, configuration stuff. They even pulled from vendor documentation, technical specifications, regulatory guidelines.
So really drilling down into the details.
Absolutely. And the constant focus was ensuring the model correctly interpreted the specialized jargon, the acronyms, and those ambiguous terms within the specific telecom context. That context is key.
So it wasn't just about quantity of text. It was about the quality and the structure, designing examples to show the relationships between ideas.
Exactly right. And a crucial part of this was creating these triplets. You have an anchor, a central piece of text, then a positive example, which means something very similar in telecom terms, and then a negative example. This is something that might seem related, but it's actually different or incorrect in that specific telecom context.
Okay. Anchor, positive, negative.
And they put a lot of effort into creating what they call hard negatives.
Hard negatives. What makes them hard?
These are negative examples that are actually very close in wording or topic to the anchor and positive, but have a subtle but critical difference in meaning within telecom. This really pushes the model, forces it to learn the fine-grained distinctions.
That makes sense. It prevents the model from just taking shortcuts based on keyword matching. Can you maybe give us an example of a telecom triplet, just to make it concrete?
Sure, yeah. Let's imagine the anchor text is something like, troubleshooting a 5G NR cell outage.
Okay, a common telecom problem.
Right. A good positive example might be investigating the cause of a 5G new radio cell being unavailable. Pretty much the same thing, different wording.
Got it. Similar meaning.
Now, a hard negative could be something like configuring parameters for a 4G LTE cell.
Ah, okay. Still about cells, still about mobile networks.
Exactly. But it's 4G LTE, not 5G NR, and it's about configuration, not troubleshooting an outage. It's related, but critically different for someone working in telecom.
I see. It forces the model to pay attention to 5G versus 4G, outage versus configuration. Those details matter.
Precisely. It's like showing the AI two very similar shades of blue and then maybe a sheet of teal to help it learn those subtle differences rather than just showing it blue and red.
That's a great explanation. So this high-quality, manually curated data set with these clever triplets was step one. What was the second key step?
The second crucial step was the deep triplet loss fine-tuning. They took that massive, carefully crafted telecom data set of triplets and used it to further train or fine-tune that base GT-Qwen2 model we talked about.
Okay, using the triplets to train? And triplet loss, that's the method.
Yeah, triplet loss is a specific technique for training these embedding models. The basic idea is to computationally encourage the model to pull the vector representations, those map coordinates of the anchor and the positive example, closer together in the embedding space.
Okay, make similar things close.
And simultaneously push the representation of the negative example further away from the anchor.
Make different things far apart. Makes sense. But you keep emphasizing deep fine-tuning. What exactly makes it deep?
Yeah, this is a really key point they make in the paper. This wasn't just tweaking a few parameters on the surface, like adjusting the final layer. They actually modify the underlying weights and parameters across all 338 layers of the transformer architecture.
338 layers. Wow.
Yeah. Think of the base model like a huge, complex machine with hundreds of interconnected gears and levers representing its language knowledge.
Okay.
deep fine-tuning wasn't just painting the outside telecom orange. It was going deep inside and actually adjusting and recalibrating almost every single gear and lever to work optimally for telecom language.
So a fundamental re-engineering almost.
That's a good way to put it. They also did something clever. They used query-like anchors in their training data.
Query-like anchors?
Yeah, basically framing some of the anchor texts like questions or search queries. This was specifically done to make T-VEC perform better on search and retrieval tasks, which is super important for, say, finding the right paragraph in a dense technical manual.
Ah, very practical. And you mentioned a formula for triplet loss. Is it worth getting into?
We don't need to dive into the math, but the core concept is pretty straightforward. The formula essentially calculates a loss, or a penalty score. It measures how well the model is doing at keeping the anchor-positive pair closer than the anchor-negative pair by at least a certain margin. If the negative isn't far enough away, the model gets penalized and adjusts its internal weights to try and do better next time.
Okay.
They use something called cosine distance or cosine similarity to measure how close or far apart the vectors are in that high-dimensional map space.
Got it. So it's a very focused learning process driven by these triplets aimed at mapping out the specifics of telecom language and doing it deep within the model structure. What was the third piece of the puzzle?
The third key piece was the development and, importantly, the public release of the very first tokenizer, specifically designed for telecom language.
A tokenizer. Right. That's the thing that breaks text down into smaller pieces or tokens that the AI can actually process.
Exactly. It's the very first step the model takes when it sees text. Now, general-purpose tokenizers, trained on broad web text, might not handle specialized telecom terms or all those acronyms very well.
Yeah, they might break up something like GNB into GNB, losing the meaning.
Precisely. Or split a technical term in a weird place. By training their own tokenizer specifically on telecom text, Nitto AI ensured that T-VEC could better understand and process these industry-specific bits of language right from the very beginning.
Like giving it a better pair of glasses specifically designed to read telecom script.
That's a good analogy, and the fact that they've made this tokenizer open source under an MIT license is a pretty big deal for the research community and anyone working with AI in telecom.
That's great. So, okay, recapping. We've got a super carefully built data set, deep fine-tuning, using this triplet loss method across hundreds of layers, and a specialized telecom tokenizer. It really sounds like a solid recipe for a model that genuinely gets telecom.
Right.
But how do we know the changes were really that deep and significant? Did they measure it somehow?
That's an excellent question. How do you quantify the depth of this transformation? Nitto AI actually did this. They calculated a mathematical measure called the L2 norm of the difference between the fine-tuned weights in T-VEC and the original weights in the base GT-Gwen2 model. They did this for every single parameter tensor that was modified.
L2 norm of the difference. Okay, sounds technical again. What does that tell us?
Think of it like measuring the total amount of change or the distance traveled for each parameter from its starting point. They found an average L2 norm difference of 0.7735 across all the adapted layers.
0.7735. Does that number mean much by itself? Is that high?
On its own, it's just a number. But in context, it indicates a pretty substantial change. It shows that, on average, the values within the fine-tuned model are significantly different from where they started in the original model. But to really illustrate this, they included a figure in their paper, Figure 1, which highlights the top 20 layers or parameter tensors that saw the most significant changes in terms of this L2 norm difference.
Okay, so where were the biggest changes happening?
What's really fascinating is that these significant changes weren't just clustered in one specific part of the model, like the very beginning or the very end. They were distributed across various components of the model's transformer blocks, things like MLP gate weights, up projection weights, down projection weights, and across numerous layers. The paper specifically mentions layers 0 through 8, for example, showing changes early on in the network.
Ah, so the changes were spread throughout the architecture.
Exactly. This widespread pattern of substantial changes really backs up their claim. It confirms that T-VEC specialization isn't just some superficial adjustment. It's the result of deep, pervasive modifications throughout the model's core structure.
It's not just a thin veneer of telecom knowledge laid on top. It's like the understanding was rebuilt from within, across the board. That is pretty significant.
It really is.
So now for the million-dollar question. Does all this deep adaptation, this fundamental reshaping, actually translate into TVEC being tangibly better at understanding telecom language in practice? What did the evaluation show?
Right. The proof is in the pudding, as they say. The results they presented are actually really compelling. First, they tested TVEC on standard academic benchmarks. These are common tests measuring how well models understand semantic textual similarity, STS tasks, and other tasks from a benchmark suite called MTEB.
Okay, general language understanding tests. How did it do?
Interestingly, TVEC performed really well here. It held its own against other strong models, and often even outperformed its own base model, the original GTK-1. In fact, looking at Table I in the paper, it achieved the highest average score across several standard STS benchmarks, like STS 12 through 16 and STS benchmark.
So it's still good at general stuff.
Yes. And Table 2 shows it achieved a leading average MTEB score of 0.825 among the compared models. This shows it maintains really robust overall language understanding capabilities.
That's actually really good to hear. It hasn't become so hyper-specialized on telecom that it's, useless for anything else.
Exactly. It suggests the fine-tuning process managed to embed the telecom knowledge without catastrophically forgetting general language skills.
Okay, but what happened when they tested it specifically on telecom language? That's the key test, right?
Absolutely. This is where TVEC just completely shines. They created a separate, held-out test set of telecom triplets, information the model had never seen during training. The test measured the model's accuracy and correctly identifying the positive telecom example as being closer or more similar to the anchor text than the negative example was.
Right. Could it tell the truly similar telecom phrases apart from the subtly different ones?
And the results were dramatic. TVEC achieved an accuracy score of 0.9380.
0.9380 out of 1. That's incredibly high.
It's exceptionally high, especially when you compare it to the other models in Table 4. Its own base model, GTK-2, scored a tiny 0.0135 on this telecom task.
Wow, 0.0135. So the base model was basically guessing randomly.
Pretty much, yes. And other strong general-purpose embedding models also scored very low, generally below 0.07.
So TVEC wasn't just a little better, it was orders of magnitude better on the telecom-specific task.
Exactly. This massive leap in performance is really the core finding. It provides clear, quantitative evidence of TVEC's exceptional, deeply ingrained ability to understand the fine-grained semantic nuances and differences within telecom language. That nearly perfect score. It really does make you stop and think about the power of this domain-specific fine-tuning approach.
Yeah, a score of over 93% versus less than 7% for even good general models. That's a genuine game changer. The numbers really do tell the story there. Did they have any visual ways to show this improvement? Sometimes charts make it clearer.
Yes, they did include a couple of very insightful visualizations in the paper, figures 2 and 3. Figure 2 compares the distribution of cosine similarities. Remember, that's the measure of closeness for the positive pairs versus the negative pairs in their telecom test set. They show this for both the base model and for TVEC.
Okay, what did those distributions look like?
For the base model, the two distributions, the similarities for positive pairs and the similarities for negative pairs, showed a huge amount of overlap.
Meaning it often rated negative pairs as being just as similar as positive pairs.
Precisely. It indicates the base model was very confused, often failing to distinguish between genuinely similar telecom concepts and related but different ones.
But for TVEC?
For TVEC, the picture in Figure 2 is dramatically different. The two distributions are much more clearly separated. The positive pairs consistently show high similarity scores, clustering together on one side, while the negative pairs show lower similarity scores, clustering on the other side. There's far less overlap.
So TVEC creates a much clearer distinction in its similarity judgments. It knows which telecom concepts are truly alike and which aren't.
Exactly. It shows a much better calibrated understanding of semantic similarity within the telecom domain.
Okay, that's Figure 2. What about Figure 3?
Figure 3 uses a visualization technique called TSNE. It tries to take the very high-dimensional embedding space, that complex map we talked about, and project it down onto a 2D map that we can actually look at. They plotted the embeddings for a set of telecom queries, their corresponding positive examples, and their hard negative examples.
And what did that 2D map show?
For the base model, the TSNE plot looked like, well, a mess.
Yeah.
All the points, queries, positives, negatives were pretty much jumbled together in one big, disorganized cloud. No clear structure.
Indicating confusion again.
Right. But for TVEC, the TSNE plot was much more organized. You could clearly see clusters forming. The positive examples tended to group tightly around their corresponding anchor queries.
Mm-hmm.
And crucially, these query-positive clusters were distinctly separated from the clusters of negative examples. It provides really strong visual evidence that TVEC has learned a much more meaningful and well-structured representation of the telecom domain in its embedding space.
That gives a really intuitive picture. TVEC is actually organizing its internal map of telecom ideas logically, while the base model's map is just chaos for this specific domain.
That's a perfect summary of what the visuals show.
Okay. One last thing I noticed in the results section, table 3, I think. It showed TVEC scoring a bit lower than its base model on a general natural language inference task, the all-NLI triplet task. Is that something we should be concerned about? Is there a trade-off?
That's a very fair point to bring up, and the authors acknowledge it. Yes, the slightly lower score on that general NLI triplet task does suggest that there might be a bit of a trade-off involved. By intensely focusing the model's learning on the very specific patterns and nuances of telecommunications language through this deep fine-tuning,
Right.
its performance on certain unrelated, very general language understanding tasks might become slightly less strong compared to models that are solely optimized for those broad tasks.
So specialization might come at a small cost to generality in some areas.
It seems plausible, yes. But arguably, this reinforces the core argument for using specialized models like TVEC in the first place. When you absolutely need the highest possible accuracy and the deepest understanding within a complex, specialized domain like telecom, that targeted expertise likely outweighs a minor dip in performance on completely unrelated general tasks.
Okay, that makes sense. It's about using the right tool for the job. You wouldn't expect a highly specialized surgical instrument to also be the best tool for, say, hammering a nail.
Exactly. It's horses for courses, as they say.
Okay, great. So wrapping this up, the key takeaway here seems crystal clear. TVEC, built through this really intensive, deep fine-tuning process using a meticulously curated telecom dataset and boosted by a specialized tokenizer,
Right.
has demonstrably achieved a significantly, almost radically better understanding of telecom-specific language compared to even strong general-purpose AI models.
That's the main message.
And it's managed to do this while still maintaining pretty strong performance on general language tasks overall.
Precisely. And the potential implications of this kind of advancement for the telecom industry itself are, well, pretty huge. Just imagine being able to perform semantic search across vast libraries of technical documents, standards, and vendor manuals with much, much greater accuracy. That could lead to way faster troubleshooting and problem solving for engineers.
Yeah, finding the exact right piece of information quickly.
Think about AI systems that can truly understand the complex language used in network alerts or fault reports, helping to automate diagnostics and root cause analysis.
Okay, speeding up network fixes.
Or even intelligent customer support bots or assistants that can actually comprehend highly technical questions from telecom professionals or even knowledgeable customers, providing much more useful answers. This could really accelerate innovation and boost operational efficiency across the board.
The potential seems really significant. And the fact that Neto AI decided to make TVEC and that specialized tokenizer open source, that's a pretty big contribution too, right?
Oh, absolutely. Releasing it under the permissive MIT license is a fantastic move for both the broader AI research community and the telecom industry specifically. It allows anyone to use it, build upon it, validate the results, integrate it into their own applications, and potentially create even more advanced tools and solutions. It really lowers the barrier to entry for applying sophisticated AI within telecom.
It's like giving the community a powerful new building block, a specialized engine they can now use freely.
Exactly. It provides a really valuable, freely available asset for driving innovation in what's obviously a critically important global industry.
So as we finish this deep dive on TVEC, it really leaves you with something to think about, doesn't it? Given how successful this kind of domain-specific, deep adaptation approach has been for telecommunications. Well, what other highly specialized fields out there, maybe medicine, law, finance, scientific research, could see similar breakthroughs using these kinds of techniques?
That's the big question.
And what entirely new kinds of AI applications might emerge as a result once we have models that can achieve this level of deep understanding in those complex niche domains? It's definitely some interesting food for thought for you, the listener. Thanks for joining us on this deep dive today.